So I want to welcome you all to Caltech, and some of you traveled great distances to get here from JPL, and others traveled across the country, and we are glad you're all here. And for this total immersion, a harmonic convergence between space people and CO2 people here at Caltech, on this nice ISRU workshop sponsored by KISS to look at ways that we can generate fuel on Mars. And I have to say my sub rosa agenda here is to see what I can learn and also how we can even carry this back to Earth, where in JCAP here at Caltech, we're working on how to reduce CO2 for the benefit of people living here on Earth before we all get up and migrate to Mars. With that, I'd like to also just say that we're going to have today sort of some framing experiences that will include some overview seminars, and to begin with some visioning exercises this afternoon that will set the stage. This whole enterprise, as I'm led to understand by my faculty colleagues who've done it before, is a little bit like designing and building a 747 while it's been cleared for takeoff and is rolling down the runway. It involves essentially a spontaneous reconfiguration and design of the agenda. So that's what we're going to be doing this afternoon. And with no further ado, let me introduce Cliff Kubiak.
So I'll get right to it, but it's a pleasure to introduce our first speaker from NASA Johnson Center in Houston, who's the first speaker in our short course. So Gerald Sanders works in the Propulsion and Power Division at NASA Johnson. He's worked in the area of in-situ resource utilization for over 20 years and is very well and widely known for his effort and work in this area. He has several titles that I'll read to you because they're really interesting. He serves as a lead for the ISRU Capability Leadership Team in the Office of Chief Engineer, lead for the ISRU System Maturation Team, and deputy lead for the ISRU tasks in the Evolvable Mars Campaign Human Spaceflight Architecture Team in the Human Exploration and Operations Mission Directorate. And this is the short version of his CV. So without any further, it's a pleasure to welcome Gerald Sanders.
So what I hope to do this morning is kind of provide a framing background for all of us as we go forward, talk about what is Mars ISRU, what have we considered up to this point, start looking at maybe some of the past and recent work that we're doing, and when you start pulling these pieces together into a system, what are some of the things that you need to think about, both from the ISRU perspective as well as the architecture perspective. So I like to start a lot of my presentations with the same chart. What is ISRU? Basically, the way we've tried to define it is any hardware or operation that harnesses and utilizes in-situ resources to provide products or services. And it can be for robotic or human exploration. And I put in-situ in italicize, because a lot of times you consider the natural resources, the Mars atmosphere, the water, whatever, but we also consider trash, crew waste, discarded hardware as potential in-situ resources as well. We typically break down ISRU into 5 or 6 different bins. The first being trying to understand what the resource is that you're going for, basically prospecting. Once you identify a potential resource you want, the next step is obviously how do I acquire that resource from the in-situ environment. Once you've acquired it, you then want to process it in some form. The first step typically is into some kind of a consumable, whether it's propellants or life support consumables or even feedstock for downstream systems. So when it comes to in-situ manufacturing and in-situ construction, we ourselves are trying to produce as much of the feedstock for those applications as well. And then there's in situ energy, which is how do I use the environment, how do I use the resources to basically increase my power capabilities, whether it's storage or generation or distribution. Two things that we always try to stress when we talk about ISRU. One is there's not just a single discipline, oh, I'm an ISRU expert per se. There are certain aspects that are unique to ISRU, but we do encompass a lot of other technical disciplines, mobility, cryogenics, crew and maintenance aspects, robotics. The other is that you can't just look at ISRU alone. By definition, we are providing a product or a service to a customer. So the customer needs to be designed around our product and services. And a lot of times what happens in the past has been you do an architecture study where you bring everything from Earth and then somebody says, well, let's throw in ISRU and see how it changes things. That never works right. You never take full advantage of ISRU when you take that approach. Working with colleagues in terrestrial mining and processing, we've learned over the years that there's something called the mining cycle, basically prospect to product. We've been doing this for centuries on Earth. So it starts with understanding those resources from a global perspective, maybe orbiters. Once you've identified regions of interest, you send your geologists, in our case, maybe rovers or hoppers or penetrators, to get a better idea of what the ore body is. Once you have an idea of what the ore body is or the resource, you then start going through the mining, the crushing, and the processing stages. I've learned also talking to the mining folks that even though you're doing all these processes, sometimes you actually have to use civil engineering, site preparation, and infrastructure emplacement as part of this as well. Miners build roads in their tunnels when they're mining, not because they like building roads, but it cuts down on the maintenance. And then you have your products that go to some customer and your waste. Well, that waste stream may be the initial product or feedstock for another system. So we try to consider all of these things when we're looking at ISRU. We're talking about Mars, so what are the Mars resources that we're interested in? The atmosphere is the one that gains the most attention. I can acquire it anywhere I am on Mars. It's got a fairly high percentage, over 95% is carbon dioxide. There are several different minerals that exist on Mars if I'm looking for feedstocks for manufacturing and construction. Do I want iron? Do I want aluminum? Do I want silicon? The other major resource besides the atmosphere that has gained a lot of attention is water. And we're understanding water more and more on Mars. I'm not a Mars scientist, so I'm not going to go into details about what the different forms are, but we find that you can get somewhere between 1.5% and 2% water almost anywhere on Mars. There are pockets and regions of higher hydrated minerals that can get you maybe up to 10% or a little bit above. And then we're finding more and more places where there's ice. Maybe several meters below the surface at the poles, or at least at where Phoenix landed, the ice was pretty near pure, dirty ice, fairly close to the surface. So which one of and then there's the slope lineae that we've seen, which may be briny water. So each one of those forms has benefits and weaknesses associated with them. So from an ISRU perspective and from a mission perspective, there are pluses and minuses for both the atmosphere and the soil processing. Strengths of the atmosphere, as I mentioned, you can get it anywhere. If my main product is propellants, 75% of my propellant masses can be oxygen, depending on the fuel I choose. So I get a huge mass leverage from just making oxygen alone. And we've been working on these techniques for years, not only in ISRU, but in life support systems and fuel cell regeneration. Some of the weaknesses is that if I'm just going for oxygen alone from the atmosphere, I don't have a fuel, so I have to bring that with me. That can be in the form of hydrogen or in the form of the fuel itself. The other thing is when I'm just making oxygen, some of the chemical processes that I'll show later on don't necessarily line up with life support. So when we're taking a bigger picture approach of Do I want to just develop one technology that can be used by multiple people? That kind of falls to the wayside a little bit. Mars water has a lot of strengths. We're learning more and more about the water. The water is pretty widespread. A lot of the techniques that we worked on in terms of excavation and processing lunar soils in the 2005 to 10 time frame are all applicable to what we want to do with the hydrated soils. And even low concentrations, I'll show in another chart, even low concentrations of water show tremendous benefits for human architectures. The weaknesses is that there are risks associated with that water. You're very site dependent potentially on the technologies you use to acquire that soil and water. There are contaminants that I'll show you that you need to consider. And the different forms of water may have implications for the search for life or planetary protection that need to be brought into consideration. So when you look at a product tree from ISRU, starting with what are the resources down to what are the products, there are different pathways you can take. The green bars are basically if I'm just going for oxygen. The interesting thing is if I throw in water as a potential resource, the number of products, both from a primary as well as a secondary perspective, start growing. And so this is kind of the force multiplier that I'm not just making methane maybe and propellants, but when I step back and I look at the architecture, some of these other products may not be worth making on their own if I was just solely doing that, but if I have the infrastructure around and the bulk of what I'm doing, making an alcohol or a plastic or a fertilizer now may start making sense. There are challenges associated with incorporating ISRU into the architectures. Most people think about the first two at the top. What are the challenges associated with the resource? Is it there? Is it where I expect it to be? Is it in the form that I expect it to be? And are there any planetary protection issues? The technical challenges, can I do this? Can I actually physically and feasibly extract the resources and process them over long periods of time? Can I get the reliability that I want? But there are operational and integration challenges that also need to be considered. I'm operating in potentially extreme environments, very dusty, temperature extremes, temperature change extremes that can occur, radiation environments. I'm also working in a microgravity or a reduced gravity environment. So the things I've learned over the years in terrestrial mining, where typically you just throw mass at your problem, if I need to dig deeper or need more force, you really can't do for ISRU and space missions. And then, as I mentioned previously, it's great to make a product, but if your customer is not willing to accept it or not designed to accept it, then you've missed out. So there are challenges of making sure that as you're developing ISRU, you're also developing these other infrastructure pieces that are designed to take that. And how do you make sure that you're working in step? I like showing this chart to managers because it shows that I know a little bit of chemical engineering. And it shows to a certain extent that there are a lot of options. So when they say, okay, I want your oxygen production plant, you kind of say, well, okay, what else might you want? And how risky do you want that technology to be? So there are low risk, low performing technologies. There's high risk, high performing technologies. So what's the balancing act as I'm developing these different chemical processes? So for oxygen production alone, there are 2 or 3 that we've considered. The favorite at the moment is solid oxide electrolyzers, as you'll hear from Mike Hecht. It's a lower technology readiness level, or TRL, than some of the others. So a fallback to that might be reverse water gas shift with a water electrolyzer. If I'm making fuels, there are different processes for making methane, for making alcohols, for making different hydrocarbons. Which one do I want? And so these are things that need to be considered from a chemical processing point of view. The last real published work that NASA did was Mars DRA 5.0. Here's a snapshot of the different ways that options for making propellants on Mars, and what are some of the chemical processes that we've considered, and which ones have we modeled. So when you're thinking about propellant production, there's the oxygen, make only oxygen. If I'm going to make the fuel, I can bring the fuel from Earth, or I can bring hydrogen to make the fuel. Or if I have both oxygen and a hydrogen source, in this case water, can I make both? And then people ask, well, hell, if there's water on Mars, why am I making methane? Why not just go to oxygen and hydrogen? We've looked at that in the past. We've looked at it recently. I don't have a chart on it, but basically the volume of hydrogen is typically 3 times the volume of any hydrocarbon fuel, so packaging becomes an issue. Hydrogen is liquefied and stored at 20 Kelvin. So the liquefaction and storage aspects of hydrogen are much more challenging than oxygen and methane. So just to answer that now, if you have questions later on, I could try to provide more feedback on that later. So we have looked at different options, and as I mentioned, in the case of oxygen only, we've looked at both the solid oxide electrolyzer and reverse water gas shift. We've looked at bringing hydrogen from Earth. If you look at Mars Direct and the early DRMs that NASA did, that was the preferred method. And then there's lately the oxygen and fuel production from water and such. So Mars DRA 5.0 basically picked oxygen only as its baseline. It was the lowest risk, lowest power approach. And as I mentioned, you get 75% of your propellant mass, so you get a huge mass leverage for minimum mission risk. We did state at the time, and the study was actually performed in 2007 and then published in 2009, we said you got to keep an eye on water on Mars. Even at 3% water, it was a lower mass than bringing your 6,500 kilograms of methane from Earth. So if you look at it, you know, here's the 6,500 kilograms. Now, if I have different forms of water, 3% or 8%, the mass drops significantly. This was done in 2007 before we really had started even developing hardware for lunar ISRU, the excavation systems and the regolith processing systems. We recently redid it for the Evolvable Mars campaign, and based on the lessons learned over the years on hardware and such, we've dropped that significantly. So the oxygen only for making about 23 metric tons of oxygen over a year and a half is about 1 metric ton of hardware. If I'm making both oxygen and fuel from water, we jump up maybe another 600 kilograms. That doesn't include this increasing the size of the power plant, maybe. That's probably another 400 to 600 kilograms, but still significantly less than the 6,500 kilograms that I need to bring in methane. And when you think about no ISRU at all, bringing 30 metric tons of propellant to Mars, that just is insane. So why do we care about making propellants? Well, it's the gear ratio. For every kilogram of propellant I make on Mars requires somewhere between 7.5 and 11 kilograms to be launched into low Earth orbit. So if I take this 23 metric tons or 30 metric tons of propellant and I start multiplying that by 7.5 to 11, I'm talking 3 to 5 SLS launches on their own, just for that aspect. So significant cost savings, significant mass leveraging savings, and it works for the moon as well when you start looking at the gear ratios of why we want to make propellants on the lunar surface or Mars surface. Now, a lot of times people say, well, why methane? And why not another hydrocarbon fuel? This fuel's better, that fuel's better. We've done that. We've looked at it, and it's not just a propulsion perspective and an ISRU perspective. You have to consider the pros and cons from both sides. So from an ISRU perspective, methane fuel is probably the easiest thing to do other than just electrolyzing water. I can make methane with a Sabatier reaction in a single pass at high purity, 99+%. It's a pretty straightforward process. We've been using the Sabatier reactors for quite some time, both outside and inside of NASA. There are other fuels like Fischer-Tropsch, I can make kerosene equivalents, I can make low hydrocarbon equivalents, but it's typically the distribution of your fuel is a little bit wider. So if I want a pure fuel or a near pure fuel, I have to do recirculation loops, adds complexity. Then from a propulsion system point of view, you have to think about things like mixture ratio, your propellant storage aspects. How clean is the propellant when you stop firing? Can I refire that engine, or is there contaminants left behind from the combustion products? How safe is it to use? Are there toxicity issues? Are there cost issues? And so when you look at the different fuels associated with it, methane fuel is about a 3.5 to 1 mixture ratio with oxygen. So when I just make oxygen alone, it's a great fuel to bring. It's very clean burning. When you look at the volume associated with methane versus oxygen at that mixture ratio, they're almost the same. So I can design the same tanks. The liquefaction temperature of methane and oxygen is similar enough that I can use the same cryogenic systems. One of the concerns with a liquid hydrocarbon is I may have an oxygen tank and a fuel tank next to each other. I may have to deal with thermal control issues of how do I prevent my liquid hydrocarbon from actually freezing when it's next to an oxygen tank. So you have to take all these things into consideration. And then there's performance. Your ISP, or your gallons per mile type of metric that propulsion folks use. And methane is one of the highest ones there. So when we look at those fuels, you have to take all those into consideration. So when I first heard that carbon monoxide might be a fuel of choice, I kind of ruled that out very quickly based on all of those aspects. It's incredibly low performing, it's got terrible density, it's got the wrong, you can't use common tanks or common liquefaction techniques. So even if it's easy to make from an ISRU perspective, the propulsion community won't accept it. So your customer won't accept it. When you look at ISRU from an end-to-end system perspective, you're acquiring the atmosphere, you have your filtration, you have some type of how do I move the atmosphere to my collection device, my separation, I have to pressurize it typically to some pressure. Chemical processes like higher pressures. The higher the pressure, the more efficient your chemical process is. So, so one might say, well, I want this to be the highest pressure possible. Well, that might make this system a lot larger than your chemical processing system. So you have to balance that out. Now, this particular process is the Sabatier making methane. So I make my methane, I have to do my different separation techniques. I dry the methane and store it. I have, if I'm excavating or trying to get water from the soils, I have different techniques to do that, all getting to my water electrolyzer and cleanup systems, eventually storage. The interesting thing to note is you can't just pick a box and say, I'm going to optimize that, because that box is influenced by the boxes around it. And those boxes that get into that subsystem, which then influences the other subsystems. So you really have to step back and look at from the system perspective, how do I optimize it? And so we have discussions, for example, about at what pressure do I want to do my Sabatier, what pressure do I want to perform my water electrolysis? Because I can have an extremely high pressure water electrolysis which may reduce my liquefaction power needs. So it's this balancing act from component to component, from function to function, that we try to consider and look at it as a whole. So what have we done? Well, we've actually spent a lot of time in the past and currently on how do we acquire CO2. You'll see this little unit compressor in Mike's presentation, but we've tried to look at different ways of how do I acquire and separate carbon dioxide from the Mars atmosphere at low pressures, at high pressures. We've looked at a lot of different CO2 processing techniques. Solid oxide electrolyzers. Some people have looked at low pressure glow discharge or plasma dissociation techniques, reverse water gas shifts, Sabatier, there's the Bosch reformers and different fuels. Recently, there's a lot of work on co-electrolysis, co-production using PEM techniques or ionic liquids that look really attractive. That you can do potentially making both oxygen and methane in one step versus having these separate boxes. Low TRL, but potentially something of interest. And then there's the different water processing techniques, high pressure and low pressure PEM electrolyzers. From a system perspective or from a soil perspective, we've looked at soil acquisition and excavation techniques, mostly for Mars, for the Moon. Now we're looking at how applicable they are for Mars. We've looked at different soil processing techniques. How do I drive those volatiles out through microwaves, open and closed reactors, downhole processing? Can I just drill a hole in the Mars surface and heat it subsurface and have the water vapors come up? These are things that we've been considering. And then, as I mentioned, there are some very interesting technologies associated with carbon-based trash and waste that are applicable to what we want to do. So we've actually built some very simple systems and tested them in the Mars environment. So we have a system perspective associated with how do I acquire the CO2 and process it into oxygen and methane. We did a lot of this work in the 90s. Recently, we've reactivated several activities associated with atmospheric processing and water processing. We've also done activities associated with hydrogen reduction from lunar regolith, which is very similar to what we might want to do to drive water off. And we're starting to now focus techniques and technologies on how do I pull out the Mars water, how do I collect it, how do I clean it up. There are a number of missions on the books. Mike will talk about the Mars 2020 mission. There's a mission that's been going on for quite some time that I started the development of the payload back in 2005 called Resolve, which is to look for ice at the poles of the Moon. There are a number of orbiters that are being proposed for lunar applications, and then the Mars 2020 orbiter is being proposed to really help identify those water resources on Mars. One of the big problems that exists is when you look at what are the needs for our missions versus what have we demonstrated, most of the work that we've done has been incredibly small scale. And the problem, I was thinking back in time, the problem is that we developed the hardware for robotic missions that we wanted to fly versus we wanted developing the hardware for the human missions that we eventually wanted to do. So we have a big gap, and all those charts that I showed you of the different techniques that we've looked at in the past and currently, they've all been at subscale. We now have to step back and look at the scaling attributes and try to bring it up to those production rates. Yeah, sorry. Oh, please. Okay. Let me see if I've... Oh, I've done something stupid here.
We'll edit it out of the video, don't worry.
Oh, yes. Okay. Full screen. Okay. There we go. Okay, so now we basically look at how does ISRU fit into the big picture, and I like to put ISRU as the center of the universe. And how everybody else is a peripheral to us. And so we start seeing is that we now have potentially a large number of customers. And how do we treat those customers? What products do those customers have that we can provide to them? And in a lot of cases, we see that there are common consumables between the customers. You know, life support folks want oxygen, water, nitrogen and argon. And they may give us stuff. You know, what can we get from that customer? So water and carbon waste from the ecosystems. Fuel cells. We can provide fuel cell oxygen and fuel, but get the water back from them for our chemical processing. Propulsion systems. We can provide propellants and purge gases. One of the things that we learned back in the Constellation days is landers never land empty, except for maybe Apollo 11. They typically always have reserves and residuals. You never want to land on an empty tank. So now I've landed on the lunar surface or Mars surface. I have free oxygen and fuel. What do I do with that? How you take advantage of those is incredibly important. And then we have our rovers and such. So one of the things we've tried to do is, if you, there's another chart I should bring. When you look at the space shuttle or the traditional way in which NASA works, every discipline is given a job, whether it's thermal control, power, propulsion, life support. And they optimize their subsystem to their requirements. They don't worry about anybody else. I'm going to design my hardware to that. So when you look at the shuttle, I had toxic propellants for OMS RCS. I had high quality, supercritical oxygen and hydrogen for my fuel cells. I had a lower grade oxygen and hydrogen for my main propulsion system. I had ammonia for my thermal control system. And then I had a different form of oxygen and water that the crew used for life support. Totally different systems, totally different technologies. So one of the things we're trying to do now is step back and say, well, if I insert ISRU into this picture and I have these commodity streams, how can I actually start maybe doing common things? Water electrolyzers, regenerative fuel cells, and ISRU all want to do water electrolysis. We all need to store our products at some point. We all need power. And so we're trying to take this approach and stepping back, and can I now start identifying common processes, common technologies? And so one of the activities that we're working on now is literally to start bringing those different communities together. How do I, if I have a fuel cell or a lander with oxygen and methane, how do I make sure that I can transfer those consumables? In what manner? If you look at launch systems, you dump. When you fill an oxygen tank or a fuel tank, you dump your excess while you're conditioning those tanks. If I've spent a year and a half making propellants on Mars, I don't want to vent my product to the atmosphere. I want to collect it and recondition it, not lose it. So what are the techniques associated with that? How do I insert ISRU and life support together? How do I make sure that the water that comes out of the Mars soil can be used for drinking? And if not, what other situations can I use it for? And with that, it looks like I got 39 seconds left. So I will end with this note, in that it's important that the technologies and the processes that you select and the elements need to be considered potentially at an architecture level now. And again, not just optimized at each individual box.